So, hello everyone, my name is Ali Salim and I'm going to be your TA for this course, CME 211. And also Matt will join me in teaching this course. You will see him next lab. I will teach you lab number 1, 3, I will write it down here. So the labs that I'm going to teach are lab number 1, lab number 3, lab number 5, and the last two labs, lab number 9 and lab number 10. So I will also write down my email. It's asalim22@uic.edu. So if you have any questions regarding these 5 labs, please shoot me an email. And otherwise, if you have any questions regarding the other labs, you can contact Matt. Of course, he will give you his contact. And if you have any question regarding the lectures itself, the assignments, you should contact directly Dr. Abu Kifa. And in case if you have any requests or permissions, please contact Dr. Abu Kifa directly. Don't send that to me because I will only refer you to Dr. Abu Kifa if you send me an email asking for that. Yes. So I'm also working as a TA and RA, so my office hours aren't fixed. So in case if you want to ask anything, you can shoot me an email. We can prepare a meeting online or in person based on your preference. Great. So our lab today will be about fluid properties. We are going to investigate several properties, which are density, specific gravity, dynamic viscosity, and kinematic viscosity for 3 different fluids. So the density, specific gravity, dynamic, and kinematic viscosity, and finally the surface tension. As I said, you are going to measure these properties for 3 fluids. These fluids are water, canola oil, and rubbing alcohol. We are not going to use any hazardous fluids, so there is no issue with handling the fluids, but try to be very careful while pouring the fluids inside the pitted tubes, so you do not drop all of them on the ground. Great. So the equipment that we are going to use today are the thermometer. This one, of course, you will come close and see. We also use several calibration cylinders. We're going to use hydrometer. Is set here. And the electronic balance to measure the acids. This one, and I will tell you how to use it now. Of course, the lab stand, stopwatch. Unfortunately, we don't have stopwatch, so we will rely on the stopwatch and our phone. And very nice surface tensionometer, this one. So this lab will be divided into 2 parts. The first part, I will try to explain the concept behind the experiment, the basic knowledge that you should have before conducting the experiment itself, and of course the second part will be performing the experiment and taking the measurements so we can calculate the properties which is required in the worksheet that you have. And if you notice, there will be several questions. Typically it's 2 or 3 questions asking you about the concept behind the experiment and also why the experiment didn't went very well, because you will notice that there might be some errors due to the human error or maybe the equipment's error. In the lab manual, you will find 2 tables. The first one is the Cannon-Vensky viscometer constant data. We will know how we will use these numbers in a while.
And the second table is the fluid properties for water, rubbing alcohol, and canola oil. Here we have the density, the specific gravity, the dynamic viscosity, and the surface tension. Great, so here we have the procedure of the first experiment, which is the picnometer density measurement. In the first experiment, we want to know the density of the three fluids, again, water, oil, and alcohol. All of us know that the density is basically the ratio between the mass of the fluid divided by, or the ratio between the mass of the fluid and the volume of the fluid. So using this picnometer, it has a predefined volume. Is shown here that this picnometer has a volume of 25 milliliters. So this is the volume. So all we want is the mass of the water. So the first step would be to measure the mass of the picnometer itself without adding any fluids. After that, we will put some fluid inside and measure it again. So if we put the difference between the first measurement and the second one, we will have the mass of the fluid, we have the mass, we have the volume, we will just divide the mass of the volume to get it. I'm just trying to pass through this very quickly right now, but of course we will do that together now. So if you have any question, you can just raise your hand and ask it. If you feel that you are not getting what I'm saying exactly, just wait for the end of the lab, or maybe once we make the experiment. If you still have a question, you can ask it later. Okay, so this is the, you can see the summary of the first experiment. We will go through it like step by step. And the second experiment, which is the hydrometric specific gravity, the purpose of this experiment is also to know the density of a certain fluid. But here we are going to follow a different approach. We are not going to use the picnometer, we are going to use something called the hydrometer. And here we have a hydrometer set. And the idea behind the hydrometer is very easy. This hydrometer here is already calibrated to be able to get the specific gravity of a certain fluid. This hydrometer has like a ruler. The ruler says that at this point, the specific gravity is 0.7, and at this point, the specific gravity is 0.8. So this thing will drop the hydrometer inside the cylinder, and it will have a certain location. So what we are going to see is where does the water surface lie, in which position. Once you know the position, you can take the measurement, and once you take the measurement, you can easily calculate the density of the fluid. Why? Because basically, the specific gravity of a certain fluid equals the density of this fluid divided by the density of water at 4 degrees. So what does that mean? The density of water at 4 degrees is already known. We know that it's approximately 1,000 kilogram per meter cube. So if you got the density of a certain fluid, and let's say it was 0.9, you can easily get the density of the fluid that you are measuring by multiplying 0.9 by 1,000, which will be 900 kilograms per cubic meter. So this is another approach to get the density of a certain fluid. The thing that you should notice in the hydrometer experiment that you have several hydrometers. As you can see here, we have 1, 2, 3, 4, 5, 6, 7, 8 hydrometers. So which hydrometer you should use? As you can see, or as I showed you 1 minute earlier, that each hydrometer is divided into a certain period or a certain interval. This one can measure the specific gravity between 0.7 and 0.8. So what if I have a fluid that has a specific gravity more than 0.8? This one won't be able to measure. So you will go through the rest of the hydrometers to check which one will work. So this means that if you are dealing with a fluid that you don't know its approximate specific gravity, you will do that by trial and error. You will use the first one, the second, the third, until you reach the one that is hanged between the fluid. It shouldn't reach the bottom. So once it reaches the bottom, this means that this hydrometer shouldn't work. You should replace it and use another. Great? Any questions? Easy. Great. So this would be the second experiment. And the third experiment is a little bit trickier than the previous two experiments, because here we have to measure the viscosity of the fluid. So what is the viscosity? I believe that Dr. Abu Kifa already explained that during his lectures, but let's go through the main concept without getting into the complicated physics behind the viscosity. Just imagine that we want to know the speed of the fluid, or the time it will take a fluid to pass through a very thin straw. Just imagine that I have a very thin straw, and you add some fluid at the top of that straw. How much time it will take to reach the bottom of the straw? So the speed or the time the fluid will take relates to the viscosity. So just imagine that you have this straw, you put some water, it will take maybe like 1 second to reach the bottom. What if you added oil? Do you think it will reach the bottom faster or slower than the water? Just think about it. Okay. I have this very thin, small straw, and I put some water here, and I can see the drop of water going down up to this point, let's say. Okay, what if I added oil? What if I dropped oil? The time it will take the oil to go through this distance will be more or less than water. I could just like pick one option and we can discuss that. I just want you to understand the physical density is very easy. Viscosity is a little bit hard. So I want you to understand what you are measuring, at least to know the importance of doing that. So the answer will be that oil will take more time to reach the end because it's very viscous. It moves very slow. So now I know that the viscosity is related to the time or to the speed of the flow of a certain fluid. So of course, the tool that we are going to use should measure the time, which is the efflux time, delta T. And we are going to use the Kinematic Viscosity, which looks as this one, to do something to measure that time. And based on that time, we know that if that time is very small, this means that the viscosity is very small. And if that time is huge, this means that the viscosity is huge. Once we get that time, we will use table number 1 to multiply the time by the constant to finally get the viscosity. As I said, we are going to do that step by step, but this is like a general overview through the lab. Great, so if you remember, at the beginning of this lab, I said we have 2 different viscosities. We have the kinematic and the dynamic viscosity. So the kinematic viscosity is called a primary dimension, which means that you can measure the kinematic viscosity. But the dynamic viscosity is a secondary dimension. What is the difference between the primary and the secondary? The primary is something that you can measure. You can't calculate the primary dimensions. You have to go to the lab, make your experiment, and get the measurement. Whereas the secondary dimensions, if you have certain values, you can easily calculate these dimensions. So knowing that there are two types of viscosities, we have the kinematic viscosity and the dynamic viscosity. We know that the kinematic viscosity can be measured using two values, or can be calculated using two measurements. The first one is the time, delta T, and the constant C. Okay, what about the dynamic viscosity? The dynamic viscosity has a certain relation with the kinematic viscosity. The kinematic viscosity equals, I'm sorry for that, let's write down the symbol of the kinematic viscosity. It is called nu, this shape, the V-like shape, while the dynamic viscosity is mu, this M-like shape. So to calculate the dynamic viscosity, you should know the relation between the kinematic and the dynamic. And the kinematic viscosity is the dynamic viscosity mu divided by rho. So if we got the mu, which is the kinematic viscosity, and if we know the rho, or the density of the fluid, we can easily calculate the dynamic viscosity. And that's why it's called a second dimension, because if you have other dimensions, you can get the dynamic viscosity from these dimensions. Is there anything that I wasn't clear about? Any questions? Any questions? Okay. So how we are going to measure the dynamic and the kinematic viscosities? I said that earlier, we're going to use the Kannon-Fensky viscometer, and there's only something I would like to express here, because it's really important, not only in this lab, but actually in every lab. You have to really be careful when you are using different units. What I mean by different units, to conduct a certain experiment and make the calculations, you should consider using a uniform dimensions. And what I mean by uniform dimensions is, we know that for the length dimension, for example, for the length dimension, we have the inch unit, the feet, millimeter, centimeters, and meters, etc. So if you are using inch as your length dimension, you can't multiply two values with different length dimensions. Of course, if you are multiplying, let's say 5 inch by 3 feet, you can't do that. This is wrong. You shouldn't do that. You should first convert inches to feet, or feet to inches. This is a very simple example, but there might be also some harder examples. As what if I have a velocity in inches per second, let's say 5 inches per second, or to make it more practical, 5 feet per second. And we have another parameter that is, let's say, the acceleration. And we have the acceleration of 10 meters per hour square. This is a more complicated task, because now we have feet and meter, second and hour, and you want to multiply these two values together. You should first unify the units. You should really understand how to do that, because if you didn't do that, all your calculation will be correct, like completely wrong. So we will go through these together, but I just want to highlight the importance of using uniform dimensions before going any further with the lab. Great, so we will do that together right now, but let's first finish that, or at least explain the last experiment, which is surface tension against air. I think you have heard before about the capillary rise phenomenon, right? This phenomenon that happened in the plants, so it can suck water from the roots to the leaves, so it can survive and do that biological process. So all of this process is done using the surface tension, or following the surface tension approach of, let's say, capillary rise phenomenon. And what does that mean? If you have a very thin tube and you have a large tube that is filled with a certain fluid, if you inserted the thin tube inside this huge tube, you will see that the fluid will rise a little bit inside the thin tube. Have you ever seen that before? Have you experienced this phenomenon? Really? I think it will be great if we saw a short video about that, so you can understand what is really happening inside the soil and the plants. Just want a very small video so you can see it. Yeah, this one should work.
Capillary rise. Fine uniform bore is called a capillary tube. When a capillary tube is dipped vertically into liquid contained in a beaker, the liquid immediately rises or falls in the tube. The rise or fall of a liquid in a very narrow capillary tube is given by H is equal
So
to.
this is the whole idea behind the capillary rise. Of course, we are not interested behind the rest of the video, but what I was saying is, and you can really try that at home, just bring
Glass tube with a very
a glass tube that is filled with water, and bring a straw, and insert the straw, you will see that is happening in front of you. So what we are going to do in the fourth experiment is to calculate something called the surface tension force. And this surface tension force is the force that is exerted on the surface of the fluid so it can make it rise inside the tube. So I think Dr. Abu Kaifa also explained that in the lecture, right? In the fourth lecture specifically. Great, so what we are going to do in the fourth experiment is we are going to fill the apparatus until a certain level, and what I mean by the apparatus, this surface tensiometer here, it's already filled to a certain level, and there is a very thin straw inserted, and this straw has a ruler behind that. So we will see that the fluid is already in a level more than this level. So what we will have to do is to get only the difference between the water level in the two tubes, and based on this value, we are going to make our calculations. So this is the main concept behind the 4 labs. I tried to explain the physical meaning of the apparatus, and the next step will be conducting the lab itself. And as you already know, for this lab, you only have 1 group, so you are lucky. It looks like you will finish maybe like 15 or maybe more than that minutes early. And if you, for any reason, need to attend with another lab, please don't contact me. I won't be able to give you a permission. Try to contact Dr. Abu Kaifa directly, and of course he will let me know if someone is have the permission to attend in another lab. But if you did that, you will have to wait for the last group, so you will lose this privilege. Okay? Great. Questions? No questions. Great. So please come forward and let's do this together. Because I won't be able to record the experiment itself, and typically I won't record the labs. I will only record the last section, which I will talk about the worksheet itself, if you missed anything. So this is like just an emergency situation because most of the students wouldn't be able to come due to the snow. So please try to come early at the beginning of the lab, okay? Great, so after getting the mass of the becnometer, the volume of the becnometer is already known, 25. We got the mass of the becnometer and the fluid. We subtracted these values to get the fluid mass. After doing that, we can easily calculate the fluid density. But there is something to consider here regarding the units issue. Let me show something to you. So because this is our first lab, I will stress a little bit on this units issue, but for the rest of the labs, I won't give it that much importance because you will already know how to handle it. So here we have the worksheet, and we already got the volume. We got the volume and the mass. We subtracted these two values to get this one, and we want to calculate the fluid density with this units. So let's see. The density rho equals the mass over volume, and the units of the mass here is grams, right? While the volume of the flow of the becnometer is in milliliter. So this will produce units of grams per milliliter, right? But it asks you to write the fluid density in kilograms per meter cube. So how can you handle that? How you will convert from grams to milliliter to kilogram per meter cube? To do that, let's first write down these two units here. And you won't convert from this to that. We already know that kilogram has 1,000 gram in it, right? And we also know that the liter has 1,000 milliliter in it. And we know that the meter cube has 1,000 liter in it. So how can we do this conversion? Easily, to convert from gram per milliliter to kilogram per meter cube, the first thing you will need to do is to convert grams to kilograms. So to do that, you will either divide by 1,000, right? Or there is also another approach, which is to multiply by 10 to the power negative 3. This is an equivalent approach. You can use either way. The second thing you should do is to convert milliliter to meter cubed. And you should consider, or you should be very careful, because we have a division mark here. So you will add a division mark, and you will add another division mark to convert from milliliter to meter cube, right? Easy. So instead of adding 2 division marks, I can only multiply by the rate between milliliter and meter cubed, which is 1000 by 1000. Why? Because meter cubed is 1000 liter and the liter is 1000 milliliter. So I will multiply by 1000 and another 1000. So the whole conversion will be, if I have milligram per milliliter and I want to convert that to kilogram per meter cubed, you will do the work and you will find that it will look like as if you multiplied by 1000 only. So I know that this might be your first time handling this units conversion, but if you did it once and you did it right, you won't have any issue after that. So I will just pause the video so it's not getting too long, and we can keep it. So if someone couldn't understand that from the first time, I will do it again. But please, if you have any question, just try to. If you don't want me to repeat it again, this is fine for me. But from your eyes, I see that you didn't get the idea. Right? Okay, I will repeat it again. So let's put some numbers so it can be more sense. Tell me the measurements that we got again. We know that the picnometer is 25 millimeter and the picnometer mass was 18.4 grams. The picnometer and fluid mass was 43 point something, 43.6, 16. So to get the mass fluid, we subtract these two numbers to get the fluid mass of 24.76 grams. So to get the fluid density, using this equation, the fluid density will be 24.76 divided by 25, which will result in 0.99 gram per milliliter. So we already know that this is the density of water, right? Okay, so let's convert it to kilograms per meter cube. I will follow the same approach but using numbers, so it should be clear now. What I will do is I will write down the 99% and to convert from grams to kilograms, I will use the multiplication approach. I will multiply that by 10 to the negative 3. So now I am done with the kilograms thing. And if I stopped at this point, the units will be kilogram per what? Milliliter. But this is not what I want. I want it to be kilogram per meter cube. So then I will try to convert this milliliter to meter cube. The only trick here is that you want to convert the units which is divided by, not multiplied by. Because here we have 0.99 grams per milliliter, not grams milliliter. This is the difference. So how you will handle this per mark or this slash is that you will first add this division. Okay? Then you want to convert milliliter to meter cube. So if I want to use the multiplication approach, I will multiply that by 10 to the negative 3, this one here, and multiply it again by 10 to the negative 3, this one here. Because liter equals 1000 milliliter and meter cubed equals 1000 liters, so meter cubed equals 1000 multiplied by 1000 milliliter. So because we have two 1000s here, and I want to divide by these, I use the multiplication approach, this one here and this one here. Because I want to convert from milliliter to meter cube. If I want to do the other way, I will multiply by 1000. So if you want to go this way, you will add this negative sign. 10 to negative sign this term. But if you want to go the other way, you will add 10 to the power of this thing without the negative sign. So if you did that using your calculator, you will find that 0.99 multiplied by negative 3 divided by 10 power negative 3 multiplied by 10 to the power of negative 3, it will show 990 kilograms per meter. So it looks very hard to do that for the first time, but it's very easy. And I'm sure that you can do that without even looking. I mean, you can do that in your head, but you will have to try that several times. So this is the idea behind converting units to answer the right questions, and the answer of the fluid density will be 99 or 990 kilograms per meter cube. So any questions? As I said, I won't go through this conversion process again, so try to do it very accurately and many times so you can handle that the next times. Okay, so let's continue our experiment by getting the, I will stop the video right now. So after getting the hydrometer reading for water, which is 0.98, and we know that the density of water at 4 degrees equals approximately 1000. To get the fluid density using the hydrometer reading, again, we know that the specific gravity is the ratio between the density of the fluid and the density of water. So to get the density of the fluid using the specific gravity, you should multiply it by the density of water at 4 degrees. So for water, it is 0.98 multiplied by 1000, and it will be 980 kilograms per meter cube. And as you can see, the first density of the water that we have measured was 990 kilograms per meter cube. And when we use the hygrometer, it says 980 kilograms per meter. So there's a difference between the two measurement approaches, and this is expected because you might get some error while getting the measurement. There might be some error in the calculation of the hygrometer. So there are a huge amount of error sources. So you should keep that in mind. Okay, let's do the other fluids. So now we got the time, the efflux time for water, and it was so for the viscosity experiment, for the viscosity. What's happening? I'm not sure what's happening, but for the viscosity experiment, we have the time, which is 33.5 seconds, and we have the constant for the tool that we used here, and it is 0.0332. So to get the kinematic viscosity, you should multiply these two numbers. So the kinematic viscosity will be 33.5 multiplied by 0.0332, which will result in 1.1122, but keep in mind the units right now, okay? We multiplied seconds by millimeter squared per second squared. So the units that we are getting here is millimeter squared per second. But this is not what it wants. It wants it in meters squared per second. So how we can do that? We have 1.1122 millimeter squared per second, and we want to convert it to meters squared per second. So what we have here is we want to convert millimeter squared to meter squared. So, and we know that the meter has 1000 millimeter in it. So to do that, we multiply by 1000, we multiply it by 10 to the power negative 3, right? Because we want to go this way. But don't forget that we have here millimeter squared. So we should also square the conversion. So we will multiply by 1000 to the negative power 6. So the kinematic viscosity will equal 1.11 multiplied by 10 to the negative 6 meter squared per second. Understood? Great, so the next thing is to calculate the dynamic viscosity with this units, Pascal second. So Pascal second is equivalent to kilogram meter second. These two units are equivalent. So let's check out how we can get the dynamic viscosity. So dynamic viscosity, mu, can be calculated using this formula, which is the dynamic viscosity, the kinematic equals the dynamic divided by rho. So the dynamic viscosity is the kinematic viscosity multiplied by rho. So for water, we know that the kinematic viscosity equals 1.11 divided by multiplied by 10 to the negative 3, negative 6, and the rho of water is approximately 990 kilograms per second. So let's put the units. So this will result in, can you calculate that? This will result in 1.099 multiplied by 10 to the negative 3. So what the unit would be? Can you figure out the units? You will also multiply the units. So let's see here. We have meter squared per second. I will try to do it with an easier way. Just imagine that it's meter squared per second multiplied by kilogram per meter cubed. So don't you think that we can get rid of this meter squared by converting this 3 to 1? And this will be the final units. It will be kilogram per second meter. And I can write it down as kilogram per meter per second, which is the units that I need, that is equivalent to Pascal second. So the final answer will be 1.099 to the power negative 3 Pascal second. Easy? Good. So let's do the same for the other experiments. This will take a huge amount of time, to be honest, but we can. Again, the time it takes the oil to go from the first mark to the second mark is 305 seconds. And the constant of the oil is 0.267. So to get the kinematic viscosity, we multiply 305 by 0.267, so it's 81.4 millimeter squared per second. So to convert that to meters squared per second, we will multiply by 10 to the power negative 3, and it will be 0.08. So it will be 0.081 meter squared per second. And if you notice that this value is very close to the value in the table, because the dynamic viscosity is approximately 0.07. Yep.
Shouldn't it be 1.4
Yep. Yeah. I'm sorry. Thanks for finding it. Great. So it's not 0.08. It's point 4.000081 meter cubed per second. Exactly. So if you multiply that by 1 thousand, or exactly 99,990 to get the dynamic viscosity, it will be 0.08 Pascal second. Right? Which is almost the same as the value in the table. In the table we have dynamic viscosity equals 0.073, and the dynamic viscosity that we measured is 0.08. So we are very close to the correct value. Any question? Sure? Great. So the first thing we did in the surface tension experiment was to get the initial fluid level in the outer tube, and it was 3.5, and the final fluid level was, remind me again, 6.5? 6.3. So 6.3. So the capillary rise is the difference between 6.3 and 3.5, which is 2.8. So knowing this 2.8, we can find the surface tension. And how to do that? I can easily give you the equation, or we can derive the equation together, because in the first question, you will see that it asks you to derive the equation by yourself. So to save you some time, I will derive it with you, okay? So the first question asks you to start with the force balance equation and derive the equation that satisfies surface tension as a function of the capillary rise. So this is a schematic of what we saw inside the tensionometer with the outer tube, and this is the water level, and inside the smaller tube, the water level is a little bit higher, and the difference between the two levels is the delta H, which is the capillary rise, 2.8. So how can we get the value of the force? Sometimes we call it sigma. How can we get the force from this system? Okay, the first thing we should imagine, or we should understand, that the force that is pulling up this column of water is the force that you are interested in. So if I was able to get the weight of the fluid, this weight will equal this force, right? So how can I get the weight of this column of water? The weight should equal the volume of the cylinder of this column of water multiplied by gamma, which is the mass, or the weight, the unit weight of the water. And how can we get the unit weight of the water? It's easily the rho multiplied by the gravitational acceleration g. So, and we know that this g is 9.81 meter per second square. So, and the volume of this cylinder is by d squared divided by 2 multiplied by delta H. There's nothing new here. We are just reviewing the basic parameters, the volume, and the volume of the cylinder, and the unit weight of the water. So the weight will be by d squared divided by 4 multiplied by delta H multiplied by rho multiplied by gamma, g, sorry. So this is the weight, and we know that from the force equilibrium that this weight should equal sigma. Okay? But actually, it's not only sigma. It's sigma cosine theta. And how is that? This is sigma. This is sigma, or F. But actually, what is pulling this column of water up is this component. And how can we get the component of F? It will be F, or sigma, cosine theta, which is the angle between the force and the straight line of the cylinder itself. We will see after a while that this cosine theta is approximately 1, so we will get rid of it, but this is the main concept here. Okay, so how can I get this sigma? Actually, this sigma is not a certain force with the Newton units. It is a force that is applied on the surface or on the whole cylinder. In other words, if this is the cylinder from above, this force is applied on every point in this perimeter. Understood? So how can I get the overall or the total force? You should multiply this sigma cosine theta with the perimeter of the circle, which is by d. So at this point, I have done the equilibrium between the weight and the force. So let's simplify this equation a little bit. Then I will have this by d squared divided by 4 delta H rho g equals sigma cosine theta by d. I can get rid of this d with the square here. I can get rid of this pi with this one. So the final equation will be d delta H rho g over 4 equals sigma cosine theta. Great. So if I want sigma to be in a certain side and the other parameters on the other side, it will be something like that. So this is the equation of the tension force. So let's try to apply this equation to the measurement that we had for water, of course. And one more thing before doing that, I said for very small theta, this cosine alpha will reach 1. Do you know that? Can you try on your calculator cosine 1 or cosine 2 or cosine 3? If the theta is very small, the result of cosine this theta will always be around 1. So we'll just get rid of this theta and let's apply in this equation the measurement that we have for water, of course. The d is the diameter. The d is the diameter of the pipe, and we have here the diameter of the pipe is 0.5, but 0.5 millimeter. Okay, so let's do it together. To calculate sigma, it would be the diameter 0.5 millimeter, and let's convert everything to meters, 25 units. So 0.5 multiplied by 10 to the power negative 3 multiplied by delta H, which is 2.8 multiplied by 10 to the negative 2, because it's in centimeters, multiplied by 990 multiplied by 981. And all of that is divided by 4. So can you give me the final answer to this equation? It will be 0.033, and the units are Newton per meter. So as you can see here, for this one, it's a little bit different than the one in the table. And this might be due to several errors, but the main idea is to do this calculation. And of course, we know that we won't be able to get the exact answer. You will do the same, because we don't have time, you will do the same for the oil and the alcohol. We already gave you the 2 levels, so you will get the final capillary rise and do the same equation. And that's it, guys, for this lab.